Swayam Prabha. Digital India. Educated India.
Welcome back to the course Geology and Soil Mechanics. So, in the last lecture we just started the discussion on stiaxial shear test, which is another laboratory test by which you can determine the shear strength parameters for a particular soil, right. And there we have seen that you have three different kinds of say triaxial test. One is the consolidated drain test, that is CD test. One is consolidated undrained test, that is CU test, and another one is the unconsolidated undrained test, that is UU test. Okay. Now, first we will discuss what is consolidated drain test, that is CD test, right. In CD test, the saturated specimen is first subjected to an all round confining pressure, say sigma 3. Okay. So, basically that sigma 3 is, I mean we are putting sigma 3, that is nothing but the minor principal stress, and once you apply the all round confining pressure, basically that means your sigma 3 is becoming the minor principal stress, because along the specimen side you do not have any shear stress applied through the sail pressure, right. So, sail water will be applying the pressure in the radial direction, and that is known as your that will be basically eventually will be becoming one principal stress. Now, we will see that. So, will be that will be becoming the minor principal stress. So, I mean first what we do, we take the saturated soil specimen, and then that saturated soil specimen is subjected to an all round confining pressure, say sigma 3, right. So, at that condition, so as confining pressure is applied, the pore water pressure of the specimen increases by UC, agreed. So, as you from your consolidation chapter, if you recall, immediately you apply some extra pressure, right. So, soil specimen was there, now you are applying some all round say sail pressure, that is sigma 3. Once you apply sigma 3, basically immediately you will be getting some increase in the pore water pressure, right, because water is incompressible. So, in the soil specimen you will be getting some increase or enhancement in the pore water pressure, that is nothing but your excess pore water pressure. Now, which can be expressed as say B, capital B is equal to UC by sigma 3, where B is nothing but the Skempton's pore pressure parameter, right. So, we will come to that point. So, basically for saturated soft soil, B is approximately equal to 1. Why B is approximately equal to 1? So, because you are not allowing the drainage, right. So, you are stopping the drainage. If you recall that spring loading spring analogy. So, if you apply the load, the pressure, okay, on the soil specimen, immediately water will try to drain out, right, but because of the valve is closed, immediately the whatever extra pressure is coming on the soil specimen, that will be taken care of by the pore fluid, that is water, right. So, therefore, for saturated soil, B is approximately equal to 1, that means UC, that is the excess pore water pressure, must be equal to sigma 3, that means there is no enhancement in the effective stress. So, whatever sigma 3 you are applying, that is completely taken care of by the water, right, which is present inside the soil specimen. So, therefore, B is approximately equal to 1. However, for saturated stiff clay, the magnitude of B can be less than 1. Okay. Now, basically this is happening, we will come to this figure, this is happening that you are applying. So, there are two steps basically happening in this consolidated drain test. In the first step, you are applying sigma 3 all round, okay, from top, from the radial direction, all round sigma 3, that means you are increasing the sail pressure, and that sail pressure will be giving you some sigma 3 all round, right. And due to that you will be getting enhancement in the UC, that is excess pore water pressure will be building up, and at that time you just open the drainage valve, right. So, once you open the drainage valve, basically whatever water will be there under excess pore water pressure inside the soil specimen, that water will be coming out or will be draining out from the drainage path, right, or the drainage pipe. Now, once the excess pore water pressure is getting dissipated, basically U c, that is nothing but the excess pore water pressure due to the application of sigma 3. Already we have seen that U c will be becoming 0 after complete consolidation under sigma 3, right, and then you are applying the deviatory stress, right, through the axial loading ram, whatever we have seen in the test setup, right. Through this you are applying sigma d, delta sigma d, and this when you are applying delta sigma d, basically at the time you are closing the drainage valve. So, whatever load you are applying, immediately it will be taken care of by the soil specimen, right, and then basically if you open the valve, then basically this sigma d, whatever excess pore water pressure will be building up, that excess pore water pressure will be draining out. So, eventually, so your due to this application of sigma delta sigma d, you have got the excess pore water pressure delta u d, which will be becoming 0 at the final state or the final situation when the consolidation will be happening, right, that is why water will be draining out. So, that is why it is known as consolidated drain test, because at the first instance when you are applying sigma 3 all round, at that time you consolidate the sample by allowing the drainage, and then during the test basically when you are applying sigma d, at that time also you are allowing the drainage, that is why it is known as consolidated drain test. Okay. Now, if the connection to drainage is opened, dissipation of the excess pore water pressure happens and thus consolidation will occur with time. So, U c will be becoming equal to 0, as I told you, right. So, once you apply the sigma 3, at that time you are you have the valve closed, drainage valve is closed, and due to that you will be getting the building up of U c, and then if you allow the drainage, that means if you open the drainage valve, right. So, at that time your U c will be dissipating out, that means the excess pore water pressure will be dissipating out, and ultimately or the eventually U c will be becoming 0. Next, the deviatory stress, that is sigma delta sigma d, is increased very slowly, very gradually. Now, you are increasing delta sigma d and you are allowing the drainage. Now, you are not closing the valve. So, you are allowing the drainage, and therefore, the drainage connection is kept open, and the slow rate of deviatory stress application allows complete dissipation of any pore water pressure that developed as a result, that is delta u d is equal to 0. Now, as I told you that if you keep the valve closed and if you apply delta sigma d, what will happen? So, some delta u d, that is some excess pore water pressure will be building up inside the soil specimen due to the application of delta sigma d, the same amount of, I mean whatever delta sigma d will be applying, the same amount of excess pore water pressure will be building up. However, you do not do that in the test, actually you keep the valve open, drainage valve open. So, as you apply delta sigma d, and this application is very slow, that means slowly you are applying delta sigma d and slowly your water is draining out. So, there is no chance of building up of excess pore water pressure inside the soil specimen. So, therefore, the whatever I mean may have happened, actually if you keep the valve closed, that is delta sigma, building up of delta u d, that will be becoming 0, because there is no excess pore water pressure getting built up inside the soil specimen due to the application of delta sigma d. Okay. So, as we have seen, so basically U c will be becoming 0, because you are allowing the consolidation, U c will be becoming 0 eventually, and then you are applying delta sigma d gradually, and also your delta u d will be becoming 0. So, that means there is no excess pore water pressure getting built up in the soil specimen due to the drainage valve is open. Now, because the pore pressure developed during the test is completely dissipated, right. So, there is no excess pore water pressure. So, the pore pressure developed, whatever pore pressure was getting developed inside the soil specimen due to the application of sigma 3 alone, and then sigma 3 plus delta sigma d along the axial direction. So, whatever is the situation, whatever is the condition, you have allowed the drainage. So, therefore, no pore pressure is getting built up, right. So, therefore, we can say total and effective confining stress, that is sigma 3, is nothing but sigma 3 prime. So, total must be equal to effective, because there is no excess pore water pressure, agreed. Okay. Similarly, total and effective axial stress at failure, it will be equal to sigma 3 plus, because sigma 3 alone is not causing the failure, as I told you, right. So, as you are applying the deviatory stress delta sigma d, and then basically you are initiating the failure, you are initiating the shear failure. So, as you increase delta sigma d, and once you reach the failure, at that time the delta sigma d is expressed is delta sigma d f. So, sigma 3 plus delta sigma d will be the axial stress, and that is nothing but sigma 1, because on the top plane you do not have any shear stress getting developed, right. So, that plane is another principal plane, and on that plane whatever stress will be, normal stress will be acting, that is nothing but the principal stress. And from the I mean mechanism, you have understood now that along the radial direction whatever principal stress was there, so that was the minor principal stress, and now you are applying sigma 3 plus delta sigma d f for at the failure, and that will be your sigma 1, that will be your major principal stress, and the total major principal stress must be equal to effective major principal stress, because you have allowed the drainage. Is that clear? Okay. So, now basically we will see that deviatory stress versus axial strain, this plot for loose sand and normally consolidated soil, and dense sand and over consolidated soil. It has been seen from the experience or from the test that loose sand and normally consolidated clay will be behaving in a very similar fashion, whereas dense sand and over consolidated clay will be behaving in a very similar fashion. So, what is that what kind of plot you will be getting in case of loose sand and normally consolidated clay? If you perform this CD test, basically you will be getting, so as you increase delta sigma d, so gradually you are increasing delta sigma d, and you will be obtaining or you will be measuring, right, axial strain, right, you can measure that, we will come to that point later on. So, basically you are applying that load, and because of that you will be getting the shortening or the squeeze or the strain in the soil specimen, right, in the vertical direction, right. So, slowly you increase delta sigma d, your axial strain is also increasing, and then it is becoming almost constant, right. Whereas, in case of dense sand and over consolidated clay, you get initial increase, and then it reaches the peak, which will be giving you the failure say stress, okay, the failure point, and after that it will be decreasing. Okay, this is the falling part. Now, basically this is a typical say Mohr Coulomb failure envelope obtained from the consolidated drain test. So, basically you will be getting two different regions. One region you will be telling about the over consolidated region, another region will be telling about the normally consolidated region. We will come to that point. So, over consolidation results when a clay is initially consolidated under an all round chamber pressure of sigma c, and which is eventually equal to sigma c prime, because the total stress and the effective stress both are equal or both are same in case of CD test, right, because you are allowing the drainage. So, there is no excess pore water pressure getting built up. So, the pore water pressure is 0. So, sigma c or sigma must be equal to sigma prime in every situation. Okay. So, over consolidation results when a clay is initially consolidated under all round chamber pressure of sigma c and is allowed to swell by reducing the chamber pressure sigma 3, which is again equal to sigma 3 prime. So, what we are doing here now, initially we are consolidating the soil specimen with an all round chamber pressure of sigma c. So, we are increasing the chamber pressure, that is a cell pressure, by an amount say sigma c, and with that pressure basically we are trying to consolidate the soil specimen, and then we are reducing, okay, we are reducing the chamber pressure to from sigma c to sigma 3. Okay. And in that reduction basically if you recall the consolidation chapter, if you increase the pressure and then if you allow the swelling, that means if you allow the unloading, then basically after reaching the sigma c, okay, you are allowing the unloading till sigma 3, right, and due to this reduction in the cell pressure or the chamber pressure, what will happen? It will swell, right. So, this I mean this swelling is allowed, and therefore, you can say the soil is over consolidated under the pressure of sigma c. So, that was the soil already experienced sigma c amount of cell pressure all round, and now it is under the pressure of sigma 3, which is lesser than sigma c. Okay. Now, the failure envelope obtained from drain test as such of such over consolidated clay specimens show two distinct branches A B and B C, right. So, you will be getting two distinct branches A B, this is A, this is B. So, A B and B C. So, you will be getting two different branches. Now, what you did, basically you consolidated the specimen, you have applied all round cell pressure by an amount sigma c prime, right. So, you had reached up to this. Now, you are performing the test by reducing sigma 3 up to this point, and then you are actually doing the shear failure, triaxial test. So, basically the soil will fail. Okay. So, this failure envelope, this is your failure envelope, molecular failure envelope. So, A B will be nothing but your failure envelope. That failure envelope will be because of your over consolidated soil. Now, if you consider the normally consolidated soil, if you say that my soil is normally consolidated soil, then the soil should be falling in this region, because this region will be experiencing the pressure which will be higher than sigma c, right. So, therefore, the soil will be behaving as normally consolidated soil. So, you will be getting two distinct zones, one zone will be talking about the over consolidation zone, another zone will be talking about the under consolidation zone. Okay. So, A B and B C, they will be basically talking about the failure envelopes, okay, for over consolidated specimen. Now, the portion A B has a flatter slope, as you have seen, portion A B has a flatter slope with a cohesion intercept, and the shear strength can be written as tau f is equal to c prime plus sigma prime tan phi 1 prime, okay, where phi 1 is this angle of internal friction, right. Now, the portion B C of the failure envelope represents a normally consolidated stage of soil, as I told you, and shear strength is given by tau f equal to sigma prime tan phi prime, where phi prime is this angle, okay, and this B C basically. So, if you continuously do the test, if you go on increasing sigma 3, say for example, if you go on increasing sigma 3, so this is your sigma 3, first sigma 3, if you increase the sigma 3, you will be getting like that, if you further increase, you will be getting like that, something like that. Okay. So, basically you will be, once you are within the over consolidated zone, you will be getting the failure envelope which is defined by line A B, and you will be getting the failure envelope which is defined by line B C under the normally consolidated region. A consolidated drained triaxial test on a clayey soil may take several days to complete, agreed, because as you know, as you have seen from our consolidation chapter, that the consolidation itself is a long process, it is time dependent process, right. So, consolidated drained triaxial test, if you want to perform on the clayey sample, it may take several days to complete, because first you have to allow the consolidation, okay, and then you will be doing the shearing. So, there are two steps involved in this test. First you do the consolidation and then you shear it and you get the failure, right. So, this consolidation process itself will take several days to complete. So, therefore, the shearing and all those things and the total, if you want to obtain the shear strength parameters, it will take several days to complete the test. For this reason, CD test is pretty uncommon. Uncommon means people do not, we will see that whatever you are getting from CD test, we can achieve those things by other triaxial tests, and those tests are comparatively quicker than CD test, because CD test the consolidation is, consolidation needs to be there, otherwise you will not be getting the proper behavior. So, for this reason CD test is pretty uncommon in the geotechnical community. So, I will stop here today. Thank you very much.